Alright, so today we're going to be talking about something called related rates. And related rates is essentially when we're given how multiple variables each are changing with respect to a common variable. And given that, we have to kind of understand and solve stuff about the dynamics of the problem. And this whole concept only gets like much easier to fathom once we kind of go over examples. So let's just go over examples. So problem 1. This problem says that there is a balloon that is being tracked 500 feet away, and the angle from tracker is increasing at a rate of pi over 4 radian per second. Or sorry, the angle is increasing at 0.14 radian per second, and angle currently is pi over 4. Find how fast is the balloon rising at the moment. So basically we're given that there's some balloon, so I'll call this a balloon, and this balloon is being tracked at a distance of like 500 feet away horizontally by this tracker, and the current angle to that balloon is pi over 4 radians, and we'll call this angle theta, and we're saying that d theta over dt, so our angle is changing at a rate of 0.14, right? So change in angle by change in time is 0.14. And given all of this, we have to find out um, how fast is the balloon rising. So if we represent the elevation of the balloon by y, we have to find dy over dt. So when I said by like all the variables, related rates is when everything is like tied together by a common like change. So everything is tied together by this dt. In this problem, all the variables, so elevation y, angle theta, are all changing with respect to time. And we're given some of those information, and we have to find out some other information. In this case, we have to find out dy over dt. And so to solve this problem, the first thing we have to do is find something that combines theta and y, right? Like what equation or what do we know about the geometry of this problem that tells us how y and theta are related? Well, one thing naturally is that we're given the like adjacent, or this forms a triangle, right? And it's a right triangle. The adjacent distance is 500, and the opposite distance is like some variable y, right? And we know that the tangent of theta, which is the angle to a balloon, is related to opposite, which is like y divided by 500, right? So now we found an equation that relates y and theta, and now we have to differentiate everything with respect to t, right? So if I were to rewrite this as 500 tan theta is equal to y, now to find out everything with respect to t, because that's the common underlying thing that ties all of this problem together, because everything is balanced by time. So finding out the derivatives of everything with respect to t, we get dy over dt is equal to 500 times secant squared theta, because that's the derivative of tangent theta, times d theta over dt. right? Because that's how theta is changing with respect to time. And so now we also have a equation relating y or dy over dt and d theta over dt, right? Um, and so with that information, now we have everything that requires us that we need to solve for dy over dt because we want to find out how fast our height's changing with time. And so we just simply do 500 times secant squared of pi over 4 times d theta over dt, which is 0.14 as given to us by the problem. We know that secant of pi over 4 is simply 1 divided by cosine pi over 4. So it is 2 over root 2, which is equal to root 2. So secant square of that is 2 times 500 times 0.14, which is equal to 1,000 times 0.14. And so that is simply 1 point, or that is simply 14 times 10, which is equal to 140. So our height is changing at a rate of 140 feet per second. So let's do another example. So here we have a car approaching a right angled intersection from the north, and another car moving east, and basically the dynamics are we have car 2 right here, so car 2, and then this is car 1, right? Car 1 is said to be 0.6 miles away from this right angled intersection, and we're said that car 2 is 0.8 miles away from the right angle intersection, or 0.8 miles to the east, and the distance between car 1 and car 2, so distance between car 1 and car 2 is increasing at a rate of 20 miles per hour. And car 1 is said to be moving here at 60 mph. And so given that, we have to find out how fast this car is moving. So we know that, so if we represent this distance as y, if we represent this distance as x, right? We know that the distance between car 1 and car 2 is simply given by the Pythagorean theorem. And so the square root of x squared plus y squared is the distance at a point. And we know that this distance is changing at a rate of 20 miles per hour. We want to find how fast dx over dt is because we want to find out how fast car 2 is going. And we know that dy over dt is equal to 60. And we know y is equal to 0.6. We know x is equal to 0.8. And in this case, since we're going like south 60 miles per hour, dy over dt is minus 60, right? Because our distance, we're measuring distance to this point. And so our distance to the center point or the intersection point is reducing as time goes on, right? So dy over dt is actually minus 60. And y is 0.6, x is 0.8. We have to find dx over dt. And so we know that if we represent distance, we'll call this d, is equal to square root of x squared plus y squared. We know that d squared, because I don't want to deal with square roots, I'll take the square. D squared is equal to x squared plus y squared. And if we were to find the related rates to this, we find the derivative with respect to t. 2d times d over dt is equal to 2x times dx over dt plus 2y times dy over dt. And so basically this is the related rates equation that we're looking at. We're given that d at this point, or we're not given d at this point, or we know d at this point is simply, also through a Pythagorean theorem, 0.6 squared plus 0.8 squared and the square root of that. And if you know the Pythagorean identity, this is simply equal to 1. So d is 1. So 2 times 1. And then we know that our distance is changing at a rate of 20 miles per hour. And the distance is increasing because this car is moving east and then this car is moving south. So because it's not getting closer to a car, in that case, it's increasing. So this is increasing by 20. And that is equal to 2 times the current distance from x. So 2 times 0.6. And then we know dx over dt is what we're trying to solve for. Plus 2 times, oh, and then this should be 0.8. 2 times 0.6 over here times negative 60. And so now we can just simply solve for dx over dt by simplifying. So 40 is equal to 1.6 times dx over dt. And then over here you get minus 36 minus 72. And so 72 plus 40 is equal to 112 divided by 1.6 is equal to dx over dt. And then if I just divide this by 4, I get 3 or 2, 28 divided by 0.4. And then this is 280 divided by 4. So 70 is equal to dx over dt. And so we know that car 2 is moving at a speed of 70 miles per hour. Let's do one final example. In this case, we have a tank that looks like this. So it's like a upside down cone. And water is entering the tank. So water enters at a rate of 9 feet cubed per minute. And currently the height of the tank is, or height where the water is, or currently the water is 6 feet deep. So the height right now is equal to 6 feet. The total height of the tank is 10 feet. The radius of the tank at the base is 5 feet. And given the fact that the water is entering at 9 feet cubed per minute, we have to find out at this moment how fast is our height increasing. So we have to find out dh over dt. So here, I mean, clearly like we're dealing with water entering, so we're dealing with the volume changing. And we know that the volume of a cone is equal to 1/3 pi r square h, right? And the only things that are changing over here is height and volume with respect to time. So we can treat r as a constant because the radius is, or actually sorry, ignore that. We know that the radius is changing with respect to time, the height is changing with respect to time, and the volume is also changing with respect to time, right? So how do we go about solving this equation or this problem given so many unknowns? One thing that we know about the properties of like a cone is that if we were to take a subsection at any point, so let's say currently this cone is filled out with some height, like 6 feet. If we were to take like a cut of the triangle that we have over here, this triangle is similar to this triangle that we have when the tank's full. And because of the fact that the triangles are similar, we know that the ratio of the height at a given point to the radius of the triangle or the radius of like the circle at that point will always be equal. What I mean is, let's say this is how the triangle looks like at one when the tank's not fully full, and then this is what the triangle looks like when the tank is fully full. We know that when the tank's full completely, the radius is 5 and the height that we have is 10. At any snapshot in time when the tank's not full, this ratio of the radius to the height will remain the same. So whatever radius we have over here at some snapshot r, that times and the ratio between that and the height h prime will always be equal to this ratio. So r over h will always be equal to 1/2. And now we can eliminate r from the equation by just substituting in the value for r, being r is equal to 1/2 h. And that kind of goes around the issue of not having anything about like how height is changing, because height, the way that the height is changing is intrinsically related to how, or that goes around the issue of not knowing how the radius is changing, because the fact that how much the radius is changing with respect to time is intrinsically related to how fast the height's changing with respect to time because of the similar triangle property. And so we can rewrite our equation for volume as 1/3 pi times 1/2 h squared times h. So volume is equal to 1/3 pi times 1/4 h cubed, and then volume is equal to 1/12 pi h cubed. And now we can go with our related rates, so dv over dt is simply equal to 1/4 times pi h squared times dh over dt. We know that the volume is changing at a rate of 9 feet cubed per minute, and it's increasing since we're pouring in water. So if I were to take this stuff over here, I get 9 is equal to 1/4 times pi, and our current height is 6, so 6 squared is 36, and we have to find out how much height is changing with respect to time, so I'm solving for that. And so this just simplifies to 9 as well, so I get 9 divided by 9 pi, which is equal to 1/pi, and that is equal to dh over dt. And so clearly we've seen how related rates is very powerful, and they can help us solve a lot of application related problems. And I guess like I never went over how like we can take an equation like v is equal to 1 over, or like with the Pythagorean, like s squared is equal to x squared plus y squared, and like I never went over how taking this and just finding out the derivatives with respect to t works out, right? And that's kind of related to how we did implicit differentiation before, right? Because what we're doing is we're doing like d over ds times ds over dt of like this s squared, and that's equal to d over dx times dx over dt plus d over dy times dy over dt, and that allows us to find, and that's the reason why we are able to say that the relationship of this equation with all respect to t is 2s times ds over dt plus, or that is equal to 2x times dx over dt plus 2y times dy over dt, because of this whole like chain rule implicit differentiation thing, right? Because d over ds is 2s, and then now you have to find out what s is changing with respect to t, so you have to multiply by ds over dt. And so I never made that explicitly clear, so if that's confusing, it's at the end. So yeah, that is related rates.